All right, problem 66 from chapter 10. I'm glad you guys threw this one in because I was going to, if you didn't. From the figure, we've got this, is it a shell? We've got a shell, right? We've got a shell that's rotating about its axis. It has a total mass m. Um, let's see if we're going to have to calculate the moment of inertia or if they give that to us in the table. On the table, axis, thin spherical shell about any diameter. The moment of inertia is 2/3 mr squared. Okay, so we got that going for us. All right, so we got the shell, we got a mass, radius with 4.5 kilograms, radius 8.5 centimeters. A massless core passes around the equator of the shell over a pulley of rotational inertia. I equals 3 times 10 to the minus 3. Radius r is 5 centimeters and it's attached to a small object, mass 0.6 kilograms. There's no friction on the pulley. Core does not slip. What is the speed of the object when it has fallen 82 centimeters after being released from rest? Use energy considerations. All right, excellent problem. So, when we start out at the beginning of this problem, the only, say there's no kinetic energy anywhere, right? Uniform spherical cell, rotate, vertical axis, frictional bearing, massless cord, over pulley. Okay, everything's at rest when we start, right? Because everything is at rest, and we're going to wait until this falls 82 centimeters, right? So if we call the initial energy of the system where it starts out at rest as 0, right? We can call that 0. I'm going to call that 0 because that generalizes the fall. And then at any point along the way, the potential energy of the ball, right? What is it, a ball? The mass, potential energy of the mass is minus the mass times acceleration of gravity, right? Mass, what are we going to call this? Block to small object. Okay, so anywhere along the way, the potential energy of the object equals the mass of the object times g times the distance it has fallen, x. All right, and we're just going to go ahead and call that negative. So the potential energy decreases as the object falls. Then there's kinetic energy of the object, right, which is 1/2 the mass of the object times the velocity of the object squared. Okay, and then there is kinetic energy of the pulley, which is 1/2 L omega squared, right? Okay, so there's a relationship between L and the velocity, not L, pardon me, I omega squared, right? Where omega, which is VR, is in fact V naught, V of the object, times the radius of the pulley, right? That's omega. So that relates to the velocity of the object. So we don't have two unknowns, we actually have one. Plus, okay, kinetic energy of the sphere, which is 1/2 I. Let me put in here because they're different. Omega of the pulley squared, right? All right, omega of the pulley is the tangential velocity of the pulley times the radius. Tangential velocity of the pulley, because this cord is going over the pulley without slipping, is the same as the velocity of the object that is falling. And here we have I of the this is I of the sphere, right? this I of the pulley, I of the sphere, omega the sphere squared, right? Okay, so omega of the sphere equals velocity of the tangential velocity of the sphere times the radius of the sphere, right? Okay, put pulley there, times the radius of the sphere, which is, again, this cord is not slipping. Cord is not slipping. So the velocity of the outside of the sphere, tangential velocity of the outside of the sphere, is again same as the velocity of the object, radius of the sphere. Okay, so initial energy starts out at 0. Then we've got minus mgx plus 1/2 mv naught squared plus 1/2 IP RP squared V naught squared plus 1/2 IS RS squared V naught squared is going to be our total energy, right? And so we can write it as 0 equals minus mg mass of the object times g times x plus 1/2 mass of the object, velocity of the object squared plus 1/2 moment of inertia of the pulley times the radius of the pulley squared times velocity of the object squared plus 1/2 moment of inertia of the sphere times radius of the sphere squared times the velocity of the object squared. Okay, so now let's see, we know everything except the velocity of the object because we want the velocity of the object when it has fallen 82 centimeters or 0.82 meters, right? So just begin putting, oh, yes, I of the sphere is per the equation in the chart, so we don't have to go do the math, 2/3 mr squared, 2/3 mass of the sphere, r of the sphere squared. All right, 2/3 mr squared, so that's 2/3 of 4.5, 2/3 times 4.5 times 8.5, 0.085 meters squared. Okay, so it equals 2/3 times 4.5 times 0.085 squared, 0.0217. 0.0217 kilograms meters squared. Okay, I of the pulley they gave us, I of the pulley is 3 times 10 to the minus 3 kilograms meters squared. All right. Radius of the sphere is 0.085 meters. Radius of the pulley is 0.05 meters. Okay. What else we need? We got that, that, and that. The mass of the object is 0.6 kilograms. Okay. Mass of the object, radius of the object, we included that. We got that. Okay, of course, G is 9.8 meters per second squared. And we're doing this at x equals 0.8 0.82 meters. I believe that is everything, right? I believe that is everything. So let's start calculating bit by bit. We have mgx is 0.6 times 9.8 times 0.82. So 4.82. 4.82 this is going to be kilograms meters squared per second squared, I believe. Meter per second squared, kilogram meter per second squared times a meter, right, equals. So 1/2 times the mass of the object, 0.6. Okay, equals 0.3 kilograms is that first coefficient. Okay, equals 1/2 times I of the pulley, which is 3e minus 3. Okay, times the radius of the pulley, 0.05 squared. Right? Go back up. Oh, yes, here I am. That's divide by. That's divide by. That's divide by. That's divide by. So, divide by. Divide by. Okay. That's why my units were so wacky. All right. So equals 1/2. All right. So the next coefficient, 3e minus 3 divided by 0.05 squared. All right. So that's 0.06. 0.06 kilograms plus. All right. Now we need 1/2 times. All right. Now we're IS, which is 0.0217 divided by radius of the sphere is 0.085 squared. 0.05, 0.01/2. Okay, which is 1.5 kilograms, all times v naught squared, v of the velocity of the object squared. Okay, so let's sum up. We have 4.82 divided by the sum of 0.3 plus 0.06 plus 1.5. 2.59. So this gives us v of the object squared is 2.59 meters squared per second squared. And so we take the square root and we get 1.61. So the velocity of the object at the 82 centimeter mark is 1.61 meters per second. And I believe that is it. Let's look over the logic real quick. Initial energy is 0. Potential energy of the object decreases as it goes down. Kinetic energy of the object is dependent on velocity. Kinetic energy of the pulley is 1/2 IP omega p squared. Kinetic energy of the sphere is 1/2 IS omega s squared. Put all that together, we have omega is VP over R, all right, V over R. So we stick that in for omega squared. We get V naught squared everywhere. We end up with IS is 2/3 MS RS squared, which is 0.0217 kilogram meter squared. Stick all the numbers in, and we end up with 1.61 meters per second. And that's it for problem 66.